In this video, we will begin looking at our Chapter 8 materials, that is, the chemistry of some corrosive materials. And so we're going to start by kind of defining, well, what is a corrosive? And so a corrosive material, as defined by the Department of Transportation, is a Class 8 hazard. Um, but what we talk about are just things that are going to have impact on metals and skin in particular. And so that's why the pictograms for the DOT, for the global harmonized, are the way they are. Now, there are no subdivisions in this class. It is just corrosive materials. And for the most part, what we're talking about are acids and bases. And so because of this, this is actually one of the largest classes of hazardous materials used in industry. Acids and bases are very common. They're found in a lot of different things. They're found in a lot of household goods. They're found in a lot of industrial goods. So corrosives play a significant role in a lot of what we see and what we do. Now, by definition, a corrosive substance is any consumer product that has a effect on your skin or your eyes. So if it can destroy the living tissue in your skin or in your eyes through a chemical action, it is considered by governmental regulations as a corrosive substance. Now, this differs slightly from a corrosive material. A corrosive material is any kind of solid or liquid that causes full skin thickness destruction of your skin at a particular site of contact in a particular amount of time, or a little bit more globally, a liquid that is able to react with steel or aluminum surfaces. So those classify as corrosive materials as well. Now, as I said before, acids and bases make up the majority of the corrosives that we are going to be studying. And so for our purposes, we are going to be defining the acid and base character of substances using something called the Arrhenius definition. Now, in the Arrhenius definition, we're talking about a very narrow focus of acids and bases. Now, there are other definitions of acid and base that are a little bit broader and include more compounds as a result. But the Arrhenius definitions are going to be important to us because they're going to be able to show us very easily, based upon chemical formula, whether or not we have an acid or a base. So under this definition, acids are substances that generate hydrogen ions in water. And so the way that we can recognize them is that their chemical formulas are going to start with an H. So if I say HCl, HNO3, HBr, C2H2O, C2H3O2. Those substances that start with a hydrogen, they are going to be acids under this definition. Bases, on the other hand, are substances that generate hydroxide ions in water. Generally speaking, these are substances that formulas end with OH. So now this isn't always true. When we get into organic materials especially, you get some hydroxyl groups that are actually not basic at all. But if we're talking about inorganic kinds of substances, things that you'd find in your home, anything that ends with a hydroxide is going to have basic tendencies to it. So calcium hydroxide, which is lime, sodium hydroxide, Li, potassium hydroxide, potash. These are substances that are bases by definition, and their formulas end with a OH group. Now, how do these acids and bases act as corrosive materials? Well, it's relatively simple. Acids and bases have a couple of things in common. We can see that acids and bases will both react with metals, and they'll both react with skin. But What makes acids different and unique is that in addition to reacting with metals and skin, they will also react with base-like solids. And so metallic oxides, these are solids with basic properties. Metallic carbonates also that way. And so these solids that have base-like properties are also going to be responsive to acids as well, in addition to metals and skin. Now, substances with base-like properties are far more common than substances with acid-like properties. And so that's why we don't see those kinds of examples here with the bases that we saw with the acids. Well, let's take a couple minutes and take a closer look at acids. So, as we mentioned before, our Arrhenius definition tells us that a substance that produces a hydrogen ion in solution is an acid. And what we can tell about acids is we can tell them apart in their chemical formulas by the presence of those acidic hydrogens. So when we have hydrogen at the front of a compound, that is a good telltale sign that it is an acid. And what's interesting about these is that even in compounds and substances that have other hydrogens in them, we will still see that acidic hydrogen put out first to let us know that there is one acidic hydrogen in this compound, and the other three hydrogens here are non-acidic. Now, it is also possible that you could have multiple acidic hydrogens, as is shown here. So phosphoric acid has potentially 3 acidic hydrogens. Sulfuric acid has potentially 2 acidic hydrogens. How quickly those get used all depends upon the environment in which they are being subjected. But it is possible to have 1, 2, or even 3 acidic hydrogens in a given acidic formula. Now, how do we get these compounds? Well, for the most part, compounds like phosphoric acid, like sulfuric acid, come about as a result of the reaction of nonmetallic oxides in water. So you take a nonmetal like phosphorus, you take a nonmetal like sulfur, you burn it in oxygen. That's how you get your nonmetallic oxide. You then take that nonmetallic oxide and react it with water. And the end result is that you get a chemical equation that, once we balance it, will yield for us phosphoric acid out of this nonmetallic oxide. Now, how do we characterize acids? We've talked about it in terms of acidic hydrogens, but we can also characterize acids in terms of strength. Now, acidic strength is not based upon the number of acidic hydrogens, and it's not based upon the number of the concentration of the acid. What it is based upon is how many ions will it break into? How many ions will it produce when it is dissolved in the water? And so, some examples of strong acids: hydrochloric acid, sulfuric acid. What we see in these cases is somewhere close to 100% conversion to H+. So every hydrogen in hydrochloric acid gets turned into H+. Most of the sulfuric acids hydrogens get turned into H+ when they dissolve in water. That's why they're strong acids. On the other hand, weak acids, such as acetic acid and hydrofluoric acid, what we see in those is usually less than 5% conversion to hydrogen ion. And so these do convert to hydrogen ions, but they do so in a very limited kind of way. And because of those limitations, what we end up seeing is much weaker acidic character compared to the strong acids. Weaker corrosive capabilities, weaker reactivity overall. Now, Another thing that we know about strong acids is that because they break apart into ions, we can conduct electricity with their solutions. We did a lab a couple of weeks ago where we took solutions, electrolytes, and hooked them up to a light bulb, and the ones that lit up were electrolytes, and the ones that didn't light up were non-electrolytes. Well, the strength of the ability to conduct electricity is what we call electrolytic character. And strong acids have strong electrolytic character. Weak acids have weak electrolytic character. And so there are 7 common strong acids. The ones that we're most familiar with are these ones: nitric acid, sulfuric acid, hydrochloric acid, and this one here is less common in household use, perchloric acid, but it's very, very common in certain kinds of industries, especially industries involving explosives, oxidizers, fireworks, those kinds of things. So these are 4 of the more common ones. Now there are other ones in here as well, but we're not going to talk too much about them. As I mentioned before, weak acids have an ability to lack in ionization. So I said less than 5%. That's a generality. In the case of acetic acid, we actually see more like 2% conversion to H plus from the acetic acid molecule. And so we end up getting electricity. We end up getting electrolytic character because we do have ions in that solution. But compared to the number of ions that we had in solution with the strong acids, it's considerably less. So this is where we'll conclude our first video. In the second video, we'll talk about some more acid characteristics, and we'll also get into some common properties of bases. Until then, have a good day.